So, welcome back to the lecture series on application of nanotechnology in agriculture. So, in the previous class I was talking to you about manganese cluster. So, I showed you the scheme of the photosynthesis and I told you that there are two photosystems, photosystem A, photosystem B, and both the photosystem receives light and both the photosystem ejects out electron, and while ejecting out electron, photosystem A as well as photosystem B gets oxidized because you are giving away electron. Okay. This electron passes through a cascade of proteins which are sitting in photosynthetic assembly or in the chloroplast. And if you look at that nano architecture of chloroplast, this is very interesting. It is something like this: thylakoid membrane, and these are all connected structure. And these are the kind of inspiration for the next generation nanotechnology. Okay, something like this, and whatever reactions I am showing here are all happening at one dot out here. The dots I am doing now, this is where these kind of reactions are happening, and the dimensions what we are talking about, if a cell is of 30 micron, this is, we are talking about something like 1 to 2 micron, the whole structure. So, automatically these are nano machines. These small ones are those small nano machines where all these reactions are happening. So, the electron then cascade through these different proteins standing at different reduction potential. If you look on your left hand side, I'm further highlighting it. Okay. Now, through this cascade of oxidation reduction, finally photosystem A out here, which was oxidized, got reduced and brought back to the ground state, but still photosystem B is in an excited state. So, photosystem B gets back to its ground state because of an electron which is donated by the manganese cluster, which strips the water. It photocatalytically kind of traps the water molecule to break it down. Now, in nature, if you look at it, all the processes which nature has been following are energy intensive processes of photocatalysis. Photocatalysis is such a powerful technique. If it is successful, then when we talk about this kind of desalination, and if you recollect, all these could really change the way we are progressing. So, now talking about photocatalysis here, this emulating manganese cluster, this is a dream. The day mankind will be emulating manganese cluster, this will be the D-Day for energy and environment. And possibly from this day on, mankind will learn one of the cheapest, or well, cheap may not be the right word to say, one of the most elegant ways by which nature does its own catalysis. Now, where we are currently, there are a lot of research happening on understanding the manganese cluster at atomic level. People are trying to crystallize this whole assembly, but the nano world currently is using one of the molecule which they are using, which draw its inspiration from here, is titanium oxide. We have talked about this titanium oxide. Today I will talk a little bit more about titanium oxide, TiO2. Okay. So, titanium oxide is a photocatalyst, and if I go back in the historical perspective of titanium oxide, then Fujishima, there are two guys, Fujishima and Honda in 1972 demonstrated, they are the first one to demonstrate that titanium oxide, which is semiconductor, TiO2 semiconductor, could split water into hydrogen and oxygen in a photoelectrochemical cell, or in a photoelectrochemical cell. And if you essentially, this work has triggered the development of semiconductor based photocatalysis for a wide range of environmental and energy application. So if you look at it, so semiconductor, which whenever we talk about semiconductor, we talk about electronics, right? And this is what I was trying to highlight in last few lectures. If you guys go back, if you see this was what I was trying to highlight. Multifunctional. So it has electronics application, titanium oxide. It could be used for water purification, and maybe it could be used for waste management, it could be used for energy. So this is when I say material should have multifunctionality. This is exactly what I meant, that this is how multifunctionality of a material could be decided. Now, if you look at titanium oxide, how it does and what are the challenges which have been met. So, I gave you this example of visible light doing this water splitting, okay, and this is all visible light of the spectrum. Now, titanium oxide has a band gap of approximately 3.2. We'll come to that, okay. So, one of the aspects regarding titanium oxide, what I wish to highlight is that titanium oxide in nature remains in three polymorphs, okay. It has anatase, rutile and bruchite phases. Anatase form, so these are called the polymorphs of titanium oxide. Anatase, rutile and bruchite. And all three polymorphs can be readily synthesized in the laboratory and are typically the metastable. Anatase and bruchite will transform to the thermodynamically stable rutile upon calcination at temperature exceeding 600 degrees centigrade. Okay. So, you realize that much of these, when you are synthesizing, they all go for a pretty high temperature. Similarly, if you look at it in all the three forms, titanium is existing in Ti4 plus form. Okay. The valency is 4 plus atoms and are coordinated to 6 oxygen atom. 4, 5, 6, and the oxygen atoms are sitting this. So, essentially what we have is TiO6. It is an octahedral geometry it follows, whereas anatase is made up of corner vertex sharing the octahedra, which form 0, 0, 1 planes. So, you do not have to go to the planes and it gets a tetragonal structure. And titanium oxide is typically, it's an N-type semiconductor, N-type semiconductor, okay. And this N-type semiconductor, due to its oxygen deficiency. So, the oxygen deficiency gives it N-type features, and it is a band gap of, as I told you, of 3.2 electron volt. For anatase it is, for anatase, and for rutile it is 3 and 3.2 for bruchite. So, it is around, you can between 3 to 3.2 electron volt. All the three polymorphs are standing at that, and all of them are, as I mentioned, all of them are N-type semiconductors. Okay. And TiO2 is most widely used investigated photocatalyst due to its high photoactivity, low cost, low toxicity, and good chemical and thermal stability. So, this is another aspect which I was highlighting, TiO2 for photocatalyst. Okay. So, these are the features which are important due to its very high photoactivity, one aspect. The second aspect, it is pretty low cost. So, in other words, it is economical to have something easily manufacturable. It has low toxicity, so handleable, and good thermal and chemical stability. These are the four features which made this a very popular material for all sorts of photocatalysis and water splitting and water purification. In the past few decades, there have been several exciting breakthroughs with respect to titanium dioxide. The major advance was in 1972, which I mentioned when Fukushima and Hondo reported the photoelectrochemical splitting of water using titanium oxide anode and a platinum counter cathode. So, basically Fujishima's and Honda's story was something like this, where you have this anode and you have a cathode. So, what essentially you had titanium dioxide electrochemical cell has titanium dioxide as anode and platinum as cathode. This is your anode. Okay. This is your cathode. So, followed by that, titanium dioxide photoelectrolysis was first used for remediation of environmental pollution. So, see, look at it. So, the same material in 1976 by Frank and Bard. So, this was another major breakthrough. So, water splitting is one of the aspect titanium dioxide does. The second thing is pollution remediation. So, basically titanium oxides photocatalysis was utilized for remediation of environmental pollutant in 1977. So, if you look at it, they are not very old. Okay. (1977) by two guys called Frank and Bard, and they reported that the reduction of cyanide CN minus in water. Okay. Frank and Bard. So, water plus CN minus, this CN minus is getting reduced in the presence of, this whole thing is happening, TiO2, and TiO2 is getting activated by light. So, this led to a dramatic increase in the research in this area because of the potential for water and air purification through utilization of free solar energy. So, your major source of solar energy is free. Other significant breakthrough included Wong in 1997, who reported that titanium oxide surfaces with excellent anti-fogging and self-cleaning abilities. So, this was another breakthrough. So, when we talk about, so again I will highlight this aspect, multifunctional, sustainable, green material, multifunctional. This is the word which is very important for you guys to understand, that this is where the future lies, something which has multiple applications. So, similarly, when we talk about the next breakthrough was 1997, where this was shown, potential for water and air purification, followed by Wong et al., who showed that titanium oxide surface has anti-fogging. So, it means you can use it in the car, anti-fogging properties, self-cleaning abilities, next thing what it has, and attributed to the super hydrophilic properties of photoexcited TiO2 surfaces. So, titanium oxide, when it is photoexcited, it is super hydrophilic. Okay. Now, photoexcited TiO2 surfaces and use of nano titanium dioxide is an efficient dye-sensitized solar cell. In 1991, there was another report, and this came from Gretzel, is in Switzerland. Gretzel cell, in whose name this is the dye-sensitized cell called Gretzel cells, or this was reported by Gretzel and Oregon, that TiO2 is, because when light is falling, it is generating an electron, and this electron could be now incorporated into a dye-sensitized solar cell. We will talk about this a little bit more, about dye-sensitized solar cell and what these are. So, these are the areas where a lot of research is happening all over the world. Okay. So, if you look at it, same titanium dioxide, it is being used for photoelectrochemical cell to split water. So, technically you can use this for hydrogen energy. This could be used as a semiconductor material. Of course, there are issues which will come very soon. Well, we will talk about the mechanism of action for pollution remediation, for Gretzel cell, and for anti-fogging and self-cleaning. So, the same material having multiple function, this is where the future lies. This is where much of these work are happening. So, in the next class we will talk about a brief mechanism of titanium dioxide and how it execute this process. Okay, thank you.